it's time to the further tutorial of the on the refrigeration cycles. So if you could find the tutorial handout in the announcement part, and if you print it out, that would be really convenient because solving all these kind of problems, we will need to check all those tables. Although I will still capture some of the tables on that, but it's better that you could learn how to practice finding all these data from these tables you need. Okay, so this time, again, just try to record this in the ecosystem that if you try to find some these refrigerant properties on the tables or graphs, you might find there are two different states. So for different states, you will find the enthalpy values are actually not the same, but that doesn't matter because, as we said, all the calculations would be about delta H. So as long as the delta H are the same, it doesn't matter which table you use. Okay, so then last time in the lecture, we did some practice about how to use the pH diagram to solve all these problems. But you also need to know that this kind of calculation can also be solved by using tables. So that would be the property tables shown in the tutorials. So today we have two practices. You can practice the first one using the tables and practice the second one using the pH diagrams. So for the first one, how to use the tables, we just quickly went through, but I guess everyone knows that as long as you get a set of data, for example, if you have a set of data says this is 10 and this is 20, and y values would be 1 and 2, then you could easily do some interpolations to find out when x value equals to 15, then what is the y values by listing all these formulas. So later you will need this expression to find out what's the exact h values in between some given data. And second one, the pH diagram. So that's something to explain before we move on to the review. And also you need to know we have two diagrams. We do the practice mainly on the pH diagram. But you should also know, so for example, in the pH diagram, your refrigeration cycle would look like this. And you can also convert all the points, like 1, 2, 3, 4, convert them to a TS diagram. So in TS diagram, you have some isobar line in different shape, but you should also know how this process, 1, 2, 3, 4, could be converted between these different tables. So first of all, make sure that you know whether this is TS diagram or a pH diagram. So don't get confused about different diagrams and different shapes of that. So that's the two diagrams of that. Then let's have a review about the refrigeration cycles. So the first one, we have an ideal vapor compression. What's the first one? Compressor. So we always start from the exit of the evaporator and go through the compressor. So can you tell me, I forgot which one. Can you tell me what's the characteristic of these two parts? Whether pressure constant or entropy constant or enthalpy constant, can you remember that? From 1 to 2. So if we're talking about compressor. So whether you have S, H, P, or T.
Size entropy.
Entropy, yes, correct. So from S1 to 2, you will have the entropy S1 equals to S2, just going through the compressor. And the next one, condenser, which parameter kept constant? 2 to 3.
Temperature and pressure.
Yes, correct. Temperature and pressure. So the pressure doesn't change because everything happens naturally, like condensation, from the vapor to liquid. But actually, a little bit change that the temperature is not always constant, because you could see from 1 to 2 get compressed, so pressure gets high, temperature also gets high, and the temperature will get to a superheated region. And if you remember what the constant temperature looks like, that would be go a little bit vertical, horizontal, and like a slope there. So you would know the temperature at point 2 is not exactly the same with temperature at 3, but the superheated vapor will be condensed to saturated liquid first, and then the saturated liquid here would be the same temperature as the, did I say saturated liquid? This part is vapor. So saturated vapor or gas would be the same temperature as saturated liquid. So there is actually two processes, not the same temperature, but in between these two, same temperature. And how about 3 to 4? Which parameter is constant? Pardon?
Enthalpy.
Yes, correct. So here, the H value, enthalpy, is the same. So you always have H4 equals to H3. So in terms of some calculations, actually you only need to find H1, H2, and H3, and then H4 would be known just from H3. So that's for an ideal compression. And the last one would be from 4 to 1. So as we said, both evaporator and condenser are actually heat exchangers. So from 4 to 1, you will see still pressure is constant. So the pressure didn't change, P1 and also P2. So from the inlet of the evaporator to the outlet, pressure constant, but the state of point 4 would be a mixture of liquid and gas, because you can see this point is located in the middle. So you're, on the left-hand side would be saturated liquid, on the other side saturated vapor. But if a point is located in the middle, that means it's a mixture of liquid and vapor. And some other terms. Are you all good with this cycle from 1, 2, 3, 4? Good. Then if a question is asking what is the heat removal from refrigerated space, what is this one referring to? Basically, all our calculation this week would be dealing with Q dot equals to the mass flow rate M dot times delta H. So when the question is asking for what's the heat removal from different space, it's basically asking you which delta H you're going to take. So can you tell me which delta H you should take for refrigerated space? The difference between 4 and 1, or 2 and 1, or 3 and 1?
4 and 1.
Yes, excellent. So for refrigerated space, we can just say it's like we want to cool down this space, so how much heat we want to remove from that. So as we said, the evaporator is installed on the side of the space we want to remove the heat from. So if the question is saying heat removal from refrigerated space, basically you just need to find out the difference between H1 and H4. So that's this part. And next one, power input, difference between which 2 points?
2 and
Yes. So just 2 and 1, because you know this part is the compression, so you just locate where is H2, H1, or H3 or H4 would be the same. So the heat rejection to the environment would be the total of these two. So you can do that either by calculating both and add them together, that would be your H high, or because you already know what's H2 and H3, so just do another step of calculation by M dot times the enthalpy difference between point 2 and 3, then you get all these values. And the COP value, do you still remember what's the COP value? I already give you like QL, W, and QH. So the COP is the ratio between which one to the other one. So the definition would be COP, the coefficient of performance, is we want to know how much cooling capacity of this system could provide comparing to the power input. So that would be simply the heat removed from the refrigerated space, QL, which is this part. Not exactly, just N times the delta H of this part, divided by the power input, which is this part. So this is a definition of COP value. If you could find out the Q dot and W, then you get the COP values. So that's basically what we need to know to solve the refrigeration cycles. Do you have any questions? No? Then I guess we could move on to some practice. Okay, so that's the first one. I didn't have the tutorial handout on this laptop, so I'm just showing you my printed out one. This is the tutorial handout, so if you go to the pages after week 2, you will see the tables saying the thermodynamics of saturated refrigerants, and also later you will have superheated refrigerant. And you should have like subcooled refrigerant, but that is a very long table. So like, for example, in this textbook, we didn't provide you the subcooled one. So that's why in the second practice, we want you to just practice on the pH diagram, because on that diagram, you can read the values from the subcooled one, but you cannot find the values for subcooled one from tables, because the table didn't give you that. So here is actually the known parameters that you know. So this is the pressure table. That's just a screen capture from the tutorial handout. And that gives you under what pressure you will have the enthalpy H or entropy S value. And also, this is saturated. So when you are doing practice, be really careful about the states. When do we need the saturated refrigerant? And another one, when do we need superheated refrigerant? So from this figure, TS diagram, you could see for an ideal cycle that you started from the exit of evaporator, it's saturated vapor. So you can just read what's the H value of 0.1 from the table. And here you have HF and H gas. So hope you know which one you should take. F would be the subscript for fluid, G would be the subscript for gas. So when you get the 0.1, you get the 0.2, and this is not located on the saturated line, which means it's a superheated state. So that means you cannot find the properties from the saturated table. Instead, you need to go to the superheated table and find out what is the H2. So here is when you need to do the interpolations, because as we just reviewed, there is a very important parameter controls where you should locate 0.2. So whether it's H, S, or temperature, I will leave it to you to try. But this table, basically you need to utilize your S values and you do the interpolation in between these two. So because the final, the goal of doing all this is to find the H values of 1 and 2. So here you should take the unknown value as the H value. So what is Y1, what is Y2? I hope you know how to do that from this one. And what is X? So I could leave it here, say X would be the S. So here should be S2 and S1. But I hope you could gain some knowledge when you are doing the practice. Okay. So have a think about these to find what is H1, 2, H3. So this is also saturated table. You can find that from this one. And when you get all the values, all the Q dot would be just mass flow rate times delta H.
Can I ask how these values in the table marry up with the H versus T graph?
H versus T.
H versus P, sorry, the enthalpy versus pressure.
This should be the same, except that they use it. If they are using the same reference state, so the table, the values would be the same as the values you read from the diagram. Should be the same.
Because if you say we're going to get 0.3 on that graph, it'd be the saturated liquid HF
Yes.
at 800, so 95.
Yes.
But then if you look on the enthalpy versus pressure graph, that value is more like 240.
So it would be like, if it's different, then we would know it's a different reference state. So one would be like 148 larger than the other one. So if you add like 148, you might just get almost the same numbers.
So the difference between, say, like, so let's do 0.14. 1 and 4. Would that change in HB 312?
212 is the lateral heat, so you should move on to the saturated vapor. That one, 239. What was the question? So you say like, with level start from?
Yeah, say the heat, the amount of heat removal would be from 0.4 to 0.1, and that change in H value would be read, is it 212, reading it off the chart?
No, 212 would be from saturated liquid to saturated vapor.
Oh,
But
that's
0.4 is in the middle. So you need to find out where 0.4 is.
Okay. Yeah, I don't know how the chart, use the chart.
some explanations to make sure you are all on the track. For point 1, we find the value just reading from the saturated table, because that point 1 is on the saturated line, so we just need to find the enthalpy value for saturated gas. But only for point 2, how do you find the point 2? The point 2 is controlled by this very important character that the entropy values is constant. So that means you also need to read what is the entropy value from point 1. So that will give you the S1 for you to do the interpolation using the superheated table to find out what is H2, because H2 is in the superheated state. So that means you cannot read that from the saturated table. And also, you didn't find the parameter that's exactly the same as the S value. So you could see the S value from point 1 is in the middle of the temperature of saturated temperature and 40. So that means, so for this one, you don't need temperature first because you get the S value. So you need to find out what is the H value in the middle by utilizing the constant X value of 1. But the following 2 points is easy because point 3 is saturated liquid. You can read from the table. And point 4, the enthalpy value is the same as 3. So as long as you get H1, calculate, do the interpolation for H2, get H3 and H4, then you can continue to find out what's the Q low or Q cold and Q high, and then make the work input. Because we have limited time for the tutorial practice, do you think it's okay that we just finish this first practice here? If you have some further calculations, you can leave it to Thursday after the lecture. But the major step is just find H1, 2, 3, 4. A little bit more calculation by doing the interpolations. If you want to take a photo, you can walk to the front and take the photo of these steps. And so that's for the first practice. Do you have any questions about this part? No? Okay, so for this one, this kind of do the interpolation and find the value was like once tested in the MIET test or the exam, not sure. And also like we could also give you a pH diagram for you to find out what's the values. So like both methods would be possible that we use to test you whether you mastered these methods. So here is the ideal refrigeration cycle. Later I will upload these tutorial slides to Canvas, so if you're worried about taking notes, so don't worry about that. The calculation details is also in the solutions. So for the first one is for that part. And you have a question too. Sorry. The second question is still the same. We are repeating the practice, but this time we try to utilize the pH diagram. And still the same, Q low is from 4 to 1, so higher H1 minus lower H4. And work input still between 0.1 and 2, and high and COP. So that's what we have practiced earlier. And now another concept to remind you is, what is the theoretical maximum COP? Because we might be dealing with ideal refrigeration cycle and also realistic refrigeration cycle. So for this one, it's actually referring to like the ratio between like Q temperature hot and temperature cold. So if you have this cycle and if you know what is the temperature of this refrigerated space, we could say low, or sometimes we say cold, so L or C. And on the other side would be the temperature hot or high. That's the temperature this refrigeration cycle is rejecting its heat to. So as long as you know the temperature from these two sides, you could imagine it as the indoor temperature and the outdoor temperature. So as long as you know a temperature of these two different environments, you can actually just utilize the temperature relationship to find out an theoretical maximum coefficient of performance. So that's the concept you are going to use later. And another concept says vapor quality. So the vapor quality is defined as the mass of vapor, so it's a mixture. So you always need to know what's the vapor quality when you know the point is a mixture. So the mixture is the mass of vapor divided the mass of the total one. But if you are using the pH diagram, that is basically still repeating all the steps like 0.1, 0.2, 0.3, and 0.4. So at the inlet of evaporator, you will see this point is in the middle of saturated liquid and saturated vapor. So this is a mixture. And what is the quality? So you could read there is a very small x starting from 0. So that means the vapor, the proportion of vapor is 0 because it's saturated liquid. And on the other side, the proportion of vapor is 100 degrees. So as long as you know where your 0.4 is located, you can just read what is the vapor quality from this diagram. Okay. So that's the only two things we need to remind you before we do the practice. And now the second practice, very similar to the first one, but the difference I hope everyone knows, I highlighted this is a commercial refrigerator. So that means all those points might shift a little bit away from this ideal compression. And from this commercial cycle, you also know that we could give you lots of information. For example, at the outlet of the evaporator, or the same as the inlet of compressor, we already tell you what's the pressure and temperature. So that means with these two parameters, you can actually locate where 0.1 is. And if you do that, you will find your 0.1 is a little bit on the right-hand side of this saturated liquid. So that means in reality, in the evaporator, all the refrigerants has been evaporated and turned into the gas phase. But the gas also continues to receive the heat. So the gas has been heated up, therefore it moves to a little bit on the right of this saturated line. Okay. So with this given information, you can locate 0.1 and 0.2 is also given. 0.3, the same pressure, so you will know that, and then 0.4. So now the question becomes, firstly, what's the quality? So we just introduced, you just read from the figure. And the second one, find the COP of the refrigerator. The only thing we need to explain to you would be this compressor is working as we have this working input of W, but meanwhile, this compressor, as it's working, it's also generate heat. So this amount of heat has actually been added in this refrigeration cycle. So how do you build the energy balance between all those two? So for example, you already know H2. You can read that from the graph, and also H1. So, and later you can find out what is the refrigerant mass. So that means you will know this part. So that's the amount of heat transfer throughout the compressor. What's the relationship between this amount of heat and W and the heat generated by the compressor. I hope you have a think about that. What's the relationship between them? So if I say this amount of heat would be equal to the work input plus the amount of heat generated by the compressor, would you all agree with that? So that basically means we have the work input to the compressor, and meanwhile the compressor is like emitting heat. So this amount of energy, both of them will contribute to the energy change between point 1 and point 2. So you will see that H2 and H1, you read from this table, actually gives you the information of both. So when you are looking for the COP value, you will need this one only. So that means, as we said, you can calculate this easily. And also this one is given as 0.45 kilowatts. So that means when you are trying to calculate W, this is no longer this value, H2 and H1. For ideal refrigeration cycle, it equals to this one. But when you have some excess of heat being generated from this, you need to exclude the heat generated from the Q in. So that's the first energy balance you need to consider. And there is another one. What is the relationship between like Q hot, Q high, Q low, and W in the work input? Actually, this one is still the same as this ideal refrigeration cycle, that the Q hot would be equal to Q low plus QW. But you will see the difference here. If I say QL equals to M H1 minus H4, is this still correct? Here the QL is referring to the total refrigeration load. So if I say, because this I just explained to you in the review, it's what I just explained exactly, but here, is this still correct? In this case, a commercial refrigerator. So you need to think about that. Because we already listed this energy balance, and for this one, you can calculate this as the energy change between 0.3 and 0.2, and also W is actually the energy change minus the work, the heat generated by compressor. So if you do this manipulation of these equations, you will get the final expression of QL as this value I just introduced in the ideal refrigeration cycle, but you have to plus Q in. So this is from the derivation of equations, but physically you could understand it in a way that when we have this refrigeration cycle, the compressor is working and generated some amount of heat, and this amount of heat also needs to be removed by this cycle. So in that way, when you are considering refrigeration load, it contains not only the amount of heat you need to remove from the environment, but also you need to remove the heat generated by the compressor as well. So these two parts, when you have a commercial refrigerator and this refrigerator is generating a heat at some heat transfer rate, these two parts of heat generation is the total refrigeration load we need to provide. So that's something we need to explain to you, because later if you look at the solutions, you will really easily get confused about that. So are you all clear with this part? Good. Okay, so I think we can continue to the practice of that one. Okay. Now you just need to use the pH diagram and use all the pressure and temperature given to you to find out what's H1, H2, H3, and H4. There is another thing you need to do the calculation is, currently we don't know the refrigerant mass flow rate. So the M dot of the refrigerant is not given to you, but it can be very easily calculated from this side. So you have the water coming in and out, so that Q would be equal to Cp m delta T. That's the amount of heat removal from the condenser. And this one also equal to the mass of refrigerant times delta H. So you know H3 and H2, so you will be able to find out what is M refrigerant from this energy balance between the heat exchange with water.
just we make the distance from the compressor and evaporator a bit shorter. Because the fluid will absorb heat from the pipes as well.
Because I suspect that that is quite complicated. So if you have it superheated in some stage, and if you follow this isentropic law, it actually would ended up at a higher condenser temperature. Although we know this would give a little bit more amount of cooling capacity, but it might make the efficiency of the condenser lower. So it would be a really complicated unless we know all the exact values and do the calculations.
What if it comes out as saturated data? This case would be optimal. Better than when it comes out as super. Not
Yeah.
more.
Yeah, because we call like the saturated line the ideal case. So of course, some other cases in real life, you might have less efficiency.
Yeah. Yeah, we keep that in mind. Thank you. Try and optimize one component, the other component will ruin everything.
That's the story of life. It's like with the toads in Australia, they're like trying to get rid of the mosquitoes or whatever after a while. Now they're going to toad invade. What I don't understand is that the engine condenses at 65 and leaves at 42. I thought that was meant to be isothermal. That's
This is not ideal.
not ideal. Alright.
Because there's a, that's what conclusion we choose. How do you call a heat exchanger when you expect the temperature to remain constant?
You get stuck in semantics in this subject, you can a bit for sure. Same thing with electrical as well. You know, whether a circuit's open or closed, you know.
Yeah. Trying to extract thermal energy from the working fluid, but the temperature, its temperature will remain unchanged.
Except in this case, it changes a bit.
This is really like it. There won't be a problem. Pressure and temperature, of course. Fractional losses as well as heat exchange. Also, another assumption is the pipes are perfectly insulated. But not the compressor. You see the 450 watts?
Yeah.
That's because the compressor. Realize you need to consider pipes, joints, everything.
I like that in the other one when they say any heat the generator that the compressor generates is going to go directly into the fluid, which is not the case. It's going to go everywhere. Compressor burn.
So
a limited time, but I think I spent enough time introducing energy balance because this part is really important. Without this part, you will really get confused about the solutions. But if you could get this part quite clearly understood, then you can continue to see the solutions we provided on the slides or the solutions. So have a further practice if you have time on that.
Can I just ask a question about this picture? It said that it entered the condenser at 65 and leaves at 42.
Yes.
But if you go, so it enters at 65.
Which one?
Leaves at 42.
Yes.
So 0.2 to 3. And then you go along. Temperature changes, pressure is the same.
Pressure is the same. Temperature you first drop to saturated gas point. So that's conjunction between the saturated mass and the gas. But between just between
But say this one says temperature.